Let's move on to coagulation. Coagulation is used to remove turbidity, color, and bacteria from drinking waters. The goal of coagulation is to change the surface charge on the particles so they can stick together to form larger particles that will settle by gravity. Although chemists tend to use the term coagulation to describe this change in surface charge and subsequent adhesion process, environmental engineers often use the term to describe the entire process by which larger particles and dissolved ions are removed by gravity settling or precipitation. There are four mechanisms that cause the destabilization of colloidal particles in natural water suspensions. First, the adsorption and charge neutralization. Second is the compression of the electrical double layer. Third is the adsorption and interparticle bridging. And last is the enmeshment in a precipitate. As shown in the figure, the negatively charged particle attracts a layer of cations that are strongly adsorbed to the surface. So this layer is called the stern layer. This is the negatively charged particle inside the circle, and the stern layer is this part here in the second layer after the circle. So this is now the stern layer. It's called the stern layer. Beyond the stern layer, there is a layer of loosely bound cations. So this one here, these are the loosely bound cations. And this layer is called the diffuse layer. The double layer, which is the combination of the diffuse layer and the stern layer, this part here, this is the double layer, has a net positive charge compared to the bulk solution. So these are short-range attractive forces, which are the van der Waals forces. These van der Waals forces allow colloidal particles in water to stick together if they can approach close enough to one another. However, as the two charged particles approach, there will be a repulsive force between them, and the interaction of the ions in their double layers may prevent them from sticking together. So that is the physics of the coagulation. Now let's move on to the coagulants. A coagulant is a chemical that is added to the water to cause the particles to coagulate. A coagulant has three key components: trivalent cation. Naturally occurring colloids are most commonly negatively charged, hence, cations are required to achieve charge neutralization. Second, non-toxic. Obviously, for the production of a potable water or drinking water, the coagulant must be non-toxic, so it should be a food grade. Third is insoluble in the neutral pH range. High concentrations of the coagulant in treated water are undesirable. Therefore, a coagulant relatively insoluble at the pH values are desired. The two most commonly used metallic coagulants are aluminum and ferric iron. So both meet the preceding three requirements: the trivalent cation, non-toxic, and insoluble in the neutral pH range. So first, let us discuss the aluminum sulfate. Aluminum sulfate can be purchased as either dry or liquid alum. So this aluminum sulfate is the commonly used alum in industries. Commercial alum has an average molecular weight of 594 with approximately 14 waters of hydration. Alum reacts with alkalinity according to the following reaction, such that each mole of alum added uses 6 moles of alkalinity, which is the hydrogen carbonate, and produces 6 moles of carbon dioxide. The preceding reaction shifts the carbonate equilibrium and decreases the pH. However, as long as sufficient alkalinity is present and carbon dioxide is allowed to evolve, the pH will not be drastically reduced. When sufficient alkalinity is not present to neutralize the sulfuric acid production, the pH may be lowered significantly due to the formation of sulfuric acid. So therefore, when our alum produces sulfuric acid, we are required to add a pH regulator. So commonly it's a sodium hydroxide. If pH control is a problem, lime or sodium carbonate may be added to neutralize the acid, thereby stabilizing the pH. Two important factors in coagulant addition are pH and dose. The optimum dose and pH must be determined from laboratory jar test. The optimal pH range for alum is approximately 5.5 to 6.5, with adequate coagulation possible at pH between 5 and 8 under some conditions. Next is iron. Ferric cations can be supplied by adding either ferric sulfate or ferric chloride. The properties of iron with respect to coagulation, efficiency, dose, and pH curves are similar to those of alum. An example of the reaction of the ferric chloride in the presence of alkalinity is shown below, and without alkalinity is shown below. If the alkalinity is insufficient, the addition of ferric chloride results in the release of 3 moles of protons for every mole of ferric chloride added. Now let's try to solve a problem related to the coagulation. So a water treatment plant with an average flow of 0.044 cubic meter per second treats its water with alum at a dose of 25 milligrams per liter. Alum coagulation is used to remove particulate matter, reduce the concentration of organic matter, and reduce the alkalinity of the water. If the organic matter concentration is reduced from 8 milligrams per liter to 3 milligrams per liter, determine the total mass of alkalinity consumed per day. So the question is asking for the total mass of alkalinity per day. Okay, let's solve the problem. We are given the dose of alum, which is the 25 milligrams per liter. Now we are going to convert it into moles per liter. So concentration of alum is equal to, so the 25 milligrams per liter. Let's convert the milligrams into grams. So 1000 milligrams is equivalent to 1 gram, divided by the molecular weight of the aluminum sulfate, which is 594.14. So 594.14 grams per mole. Okay, so cancel milligrams, cancel grams. So the concentration of alums in mole per liter is 4.208 times 10 raised to negative 5 moles per liter. Now, the next step we're going to do is to solve the alkalinity. So for the alkalinity, this is equal to the concentration of the alum, which is the 4.208 times 10 raised to the negative 5 moles per liters. In our previous discussion, 1 mole of alum produces 6 moles of the hydrogen carbonate, which is our source of the alkalinity. So 1 mole of alum per 6 moles of hydrogen carbonate. Okay? And then we have 2.52 times 10 raised to the negative 4 moles per liter of hydrogen carbonate. So it is also equivalent to 2.52 equivalents per liter of alkalinity. Okay, so we already have the alkalinity. The next step is to solve for the total alkalinity removed. So for the total alkalinity removed, total alkalinity removed, it is equal to the alkalinity, which is 2.52 times 10 raised to the negative 4 equivalents per liters times the average flow of 0.044 cubic meter per second. Then we need to convert cubic meter into liters. So 1 cubic meter is equivalent to 1,000 liters. And we need to convert 1 day into seconds. So 1 day is equivalent to 80, 86,400 seconds. Okay, so cancel everything here. Cancel liters, the cubic meter, the seconds. And we now have the equivalence per day of 958 equivalents per day for the total alkalinity removed. Now, the problem is asking for the total mass of the alkalinity. So we are going to convert these equivalents per day into kilograms per day. So we know that the molecular weight of the hydrogen carbonate is equal to 61 grams per mole, which is also equal to 61 grams per equivalence. So we can now solve for the total mass of the alkalinity consumed. So this is equal to the 958 equivalents per day times the molecular weight of hydrogen carbonate, which is 61 grams per equivalence. And now cancel equivalence. And we have 58.438 kilograms per day. So this is the total mass of alkalinity consumed per day. Now let's try to solve another sample problem. A coagulation treatment plant with a flow of 0.044 cubic meter per second is dosing alum at 33 milligrams per liter. No other chemicals are being added. The raw water per suspended solids concentration is 47 milligrams per liters. The effluent per suspended solids concentration is measured at 10 milligrams per liter. The sludge solids content is 1.05%, and the specific gravity of the sludge solids is 2.61. What volume of sludge must be disposed of each day? Okay, so the problem is asking for the volume of the sludge that must be disposed each day. First, let us illustrate the problem. Say we have a basin here. Volumetric flow in is 0.044 cubic meter per second. And the alum introduced here is equal to 33 milligrams per liter. Now for the suspended solids here, 47 milligrams per liter. So at the bottom is the sludge flow or the volumetric flow for the sludge, and for the volumetric flow out, we have the suspended solids of 10 milligrams per liter. So the first thing we are going to do is to conduct a component material balance for the suspended solids. Okay, so we know that mass in is equal to mass out, and we can now solve for the suspended solids removed per day. So for the suspended solids removed per day, solids removed per day, it's equal to the mass in, which is 47 milligrams per liter, minus mass out, which is 10 milligrams per liter. So that's milligrams per liter. So it's equivalent to 37 milligrams per liter for the suspended solids removed. Now, the next step we are going to do is to find the mass of the suspended solids removed. So mass of suspended solids removed is equal to the average volumetric flow, or the coagulant plant, or the flow into the coagulant treatment plant, 0.044 cubic meter per seconds, then multiply by the suspended solids removed per day, which is 37 milligrams per liter. Then we need to convert liters into cubic meters. So 1,000 liters is equivalent to 1 cubic meter. And convert 1 day into seconds. So it's 86,400 seconds for 1 day. And we need to convert milligrams into kilogram. So 1 times 10 raised to the 6th power milligram is equal to 1 kilogram. So cancel milligrams here, liters, cubic, then seconds. So we have now the mass of suspended solids removed, 140.66 kilograms per day. The next thing we are going to do is to relate the moles of alum into the moles of aluminum hydroxide. So we know that for every mole of alum added, we can produce 2 moles of aluminum hydroxide. So for every mole of alum added, 2 moles of aluminum hydroxide produced. So we have 2 moles of aluminum hydroxide for every mole of alum. So calculate for the concentration of the aluminum hydroxide precipitate. So it is equal to the 33, which is the alum dose, 33 milligrams per liter, divided by the molecular weight of the alum sulfate, or the aluminum sulfate, 594.14 grams per mole. Then we need to convert milligrams into grams. So 1,000 milligrams is equivalent to 1 gram. And for every mole of alum, we have 2 moles of aluminum hydroxide. So it's equal to 1.11 times 10 raised to the negative 4 moles per liters for the concentration of aluminum hydroxide. Now we are going to calculate for the mass of dry aluminum hydroxide sludge. So for the mass of dry aluminum hydroxide sludge is equal to the concentration of our aluminum hydroxide precipitated, which is 1.11 times 10 raised to the negative 4 milligrams per liter, times for the molecular weight of aluminum hydroxide, it's 78 grams per mole. Then we need to convert milligrams into grams, and To get the mass of dry aluminum hydroxide, we need to multiply it to the volumetric flow, which is 0.044 cubic meter per seconds. Then we need to convert the cubic meter into liters. So 1 cubic meter is equivalent to 1,000 liters. And 1 day is equivalent to 86,400 seconds. Now, a last conversion is the milligrams into kilogram. So 1 times 10 raised to the 6th power milligrams is equivalent to 1 kilogram. Okay, so cancel everything here. So this is equal to 32.91 kilograms per day. Okay, so this is not milligram, this is moles per liter. So cancel it. So mass of dry aluminum hydroxide is 32.91 kilograms per day. So for the total sludge production, we have the 140.66 plus 32.91 kilograms per day is equal to 173.57 kilograms per day of sludge production. So the question is asking for the volume, total volume. So now we are given the solids content as percent is equal to the mass of the solids divided by the mass of the solids plus the mass of water, so times 100. Since we have 1.05%, so just plug in here 1.05 is equal to the mass of solids is 173, the total sludge production 0.57 over 173.57 plus the mass of water times 100. So for the mass of water, we have 16,356.91 kilograms per day. So now we can solve for the total volume. We know that volume is equal to mass divided by its density. So for the total volume, it's equal to, for the total volume, it's equal to the volume of the solids plus volume of water. We have the mass of solids 173.57 kilograms per day divided by 2.65 for the specific gravity times the density of water 1000 kilograms per cubic meter plus the mass of the water is 16,356.91 kilograms per day divided by the density of the water, which is 1000 kilograms per cubic meter. So for the total volume, we have 16.4225 cubic meter per day. So this is now our final answer.